Hello, good morning students. I am Dr. SUNITA TANDON from RR College, Alwar. Today I am going to start the lecture number 3 of the chapter Acid Rains. This is a general paper of environmental chemistry. In the last two lectures, we have studied about what is acid rains and what are the different acids which are formed due to impurities in the environment which make the rain acidic. And in that case in that process we have studied about firstly the formation of sulfuric acid, and we have studied the three methods of formation of sulfuric acid. In the first we studied the formation of nitric acid, then we have studied the method of formation of sulfuric acid. In formation of sulfuric acid we have studied the three methods. Now two methods are remaining which we will start today. Oxidation of sulfur dioxide by ground state oxygen atom, oxygen in the 3p state. Ground state means it is the lowest energy state. SO2 combines with ground state oxygen atom in the presence of third body to form sulfur trioxide, and the rate constant K for this reaction is 3.3 into 10 to the power minus 14 centimeter cube mole inverse centimeter second inverse. Concentration of ozone atom in ambient air is only equal to or less than 10 to the power of 5 atoms centimeter cube, while lifetime of SO2 in above reaction is more than 9.6 years, making insignificant contribution to the oxidation of SO2. However, if high NO2 concentration is present in sunlight, significant amount of O3 may be formed. This may lead to measurable rate of SO2 oxidation. Fifth method is catalytic oxidation of SO2. Sulfuric acid can also be formed in a heterogeneous process when the required reactants are available in cloud droplets. The formation of sulfuric acid is slow in clean air, but it is catalyzed by aerosol containing metal ions of copper 2, iron 2, Mn2 and oxides of lead 2, calcium 2, chromium 3 and the aluminium 3. As a result, sulfur dioxide combines with oxygen half to form in presence of water to form sulfuric acid, and heat. This is exothermic reaction is 600 kilojoules. The presence of hydrocarbons and NOx speed up the oxidation rate of the reaction. Even soot particles are also known to be strongly involved in catalyzing the oxidation of sulfur dioxide. Building surfaces may also act as catalytic center. Increase in acidity inhibits the reaction, which proceeds best in neutral or alkaline medium. Since the reaction produces sulfuric acid, it slows down as acid accumulates. The formation of SO3-2 and HSO3-1 from sulfur dioxide in water are suppressed by increasing acidity driving reaction 1. One reaction driving reaction is SO2 combined with half oxygen molecule with water to form sulfuric acid, and the heat is evolved towards left, decreasing the solubility of sulfur dioxide in the droplets. The solubility of sulfur dioxide in water is a function of pH, which can be explained by the following equilibria. First is sulfur dioxide reacts with water to form aqueous sulfur dioxide. This is a reversible reaction. As sulfur dioxide aqueous again reacts with water to form H2SO3 again aqueous. H2SO3 aqueous reacts with water to form HSO3 and hydronium ion H3O positive. Now HSO3 ions combines with water to form sulfur trioxide SO3-2 and H3O. Now 2HSO3 which are formed during these reactions, they are converted by in equilibrium stage to S2O5-2 and water. Thus sulfur component in water are either covalent sulfur dioxide aqueous and H2SO3 or ionic sulfur trioxide HSO3- and S2O5-. Ionic species are polar, and so they are more soluble in water. sulfur dioxide solubility rises above pH 4 but drops markedly below pH 4. Addition of base like ammonia accelerates the reaction rate by reducing the acidity and forming main sulfate aerosols, that is ammonium sulfate NH4 whole twice sulfur dioxide and NH4HSO4. The reaction mechanism probably involve oxidation of sulfate species rather than sulfur dioxide. So HSO3 minus combines with water and gives 2 electrons to form HSO3 minus, HSO4 minus and 2 protons. 4 protons combine with oxygen and 4 electrons to form 2 water molecules. HSO3 minus then react with oxygen to form HSO4 minus, 2 HSO4 minus ions. Catalyst acts as an oxidation and may increase the rate of reaction from 10 to 100 times. The oxidation of sulfur species take place within the water droplets. HSO4 aqueous combine with hydronium ion aqueous to form H2SO4 aqueous and the water molecule. Ozone and hydrogen peroxide also act as oxidants. HSO3 aqueous combines with ozone to form sulfate ion plus hydronium ion, both aqueous plus oxygen. SO3 minus aqueous ions combines with oxygen to form sulfate ions aqueous and oxygen. HSO3 aqueous combines with hydrogen peroxide aqueous to form HSO4 aqueous and water. It has been observed that below pH 5.5, H2O2 is the primary oxidant, and above pH 5.5, ozone becomes more important. Acid rain with pH 4 is 10 times as acidic as normal rain with pH of 5 and 100 times more acidic than distilled water than pH 7. Now there is a sixth method of homogeneous aqueous phase reaction of sulfur dioxide by which sulfuric acid is formed in the environment. The presence of droplets. The presence of droplets. The presence of droplets in the form of aerosol, cloud, fog, and rain is in the troposphere offers another phase in which sulfur dioxidation may occur. Thus, SO2 gas dissolves in water to set up the equilibrium. Sulfur dioxide gas combines with water, and this is a reversible reaction to form sulfur dioxide point H2O. This is in equilibrium with HSO3 plus H ions. Two HSO3 ions form sulfur trioxide plus H ions HSO3 minus ions. As a result, dissolved sulfur dioxide contains 3 species, namely hydrated sulfur dioxide, bisulfite ion HSO3 and SO3 minus 2 ions. The predominant form depends on the acidity of solution in the gas phase. SO2 concentration range from 0.2 to 200 ppm and over pH range of 0 to 6 in concentration from 10 to the power of -3 to -9 to -3 moles per liter. Oxidation state of S, that is +4, is often used to denote different forms of dissolved sulfur dioxide. Sulfur 6 is equal to sulfur dioxide point H2O plus SO3 plus SO3 minus 2. Rates of various aqueous phase reactions show different dependence on pH. Some have rate coefficients and increase with increasing pH, for example ozone, while others like H2O2 show the opposite trend. Reactions in droplets. The major oxidation species in water are ozone and H2O2 both have a various potential. Ozone absorbs light in the 360 nanometer range in presence of water and from H2O2 plus oxygen. Photolysis of H2O2 gives hydroxyl free radicals. So H2O2 absorbs light equal to 360 or less than 360 nm and is converted into 2 hydroxyl layer. The major loss processes of ozone 3 and H2O2 in droplet will depend on the presence of concentration of other species in solution. O3 can react with OH and H2O minus to produce superoxide ions. Ozone reacts with OH ions to form H2O plus oxygen. Ozone reacts with OH ions to form H2O plus oxygen. And ozone reacts with HO2 to form OH plus 2H2O. Similarly, ozone reacts with HO2 HO2 minus ion to form HO oxygen minus 2 and oxygen. Rate constant for the second and third reaction is 1.1 10 to the power of 8 moles per second, and K for the third reaction is 4 into 10 to the power of 6 moles per second. In urban area, nitric acid and sulfurs 4 are also present. Ozone reacts with other species also. Ozone reacts with HSO3 plus OH ions to form sulfate and water molecules and oxygen. From pH 1 to 3, rate cannot increase by one order in magnitude. The photolyzed solution of hydrogen peroxide predominates over photolysis oxidation of sulfur 4 by ozone. Occurs via free radical pathway since ozone can provide OH free radical in aqueous solution which may oxidize sulfur dioxide as follows. HSO3 reacts with OH free radical to form H2O plus SO3 minus. SO3 minus 2 reacts with oxygen to form SO5. S2SO5 reacts to form 2SO4 plus oxygen. SO4 minus 2 reacts with water H2O2 to form HSO4 and HO2 ions. HSO3 ions reacts with 2NO2 plus water to form hydronium ion 2NO2 plus sulfur dioxide. Comparison between sulfuric acid and nitric acid. Once formed in atmosphere, sulfuric acid and nitric acid show quite different behavior. Nitric acid is more volatile and thus exists in gas phase, while sulfuric acid has a very low vapor pressure under ambient conditions, hence exists in the form of particles. Second, if deposition of sulfur dioxide on surface is occurring at a constant rate, in competition with its oxidation, more of sulfur dioxide will end up as deposit and less transformation into sulfuric acid in air. However, no such deposition of NOx is observed. The reactions of nitric acid and sulfuric acid are intertwined via OH free radical and other oxidant involved in converting NOx and SO2 into acids. For example, where significant concentration of NOx and SO2 are present, increasing NOx will decrease the gas phase rate of formation of sulfuric acid. Because excess of NOx increases, the rate of reaction is 4.48 times the lowering the concentration of gas phase OH free radical which causes oxidation of sulfur dioxide. Now today we have completed the reaction of formation of sulfuric acid in the environment. Now we will study the rest of the things, role of wind in acid air, adverse effects of acid rain, etc.